Yeah, I'm going to talk about Servant, an API description library. My name is Arian van Putten. I am a master's student at Universiteit Utrecht in the Netherlands, part of the software technology group, and we do programming languages, DSLs, type theory, semantics, all that kind of stuff. It's basically the Haskell group, so to say. I started experimenting with Servant, I think 2 years ago, or 1.5 years ago, and then a year ago I started contributing after I met some of the guys at the Haskell Exchange. They're a very jolly bunch. You should join the IRC channel. It's #Servant on the Freenode network. Yeah, I hope to enlighten you today about the wonders of Servant. So, a small agenda. First, we're going to talk about what is API. It's kind of useful when describing an API library. And then we're going to answer the question, where is an API? Which sounds a bit weird, but it will become clear soon. Then I'll talk about Servant. We'll talk about deriving documentation in Servant, writing an API server in Servant, deriving clients, and we'll look at other cool derivations and tricks that Servant gives us, and then we'll have some time for questions and stuff. So, what is a web API? Someone maybe shout some words. It's nice, some human interaction.
Communication, not a protocol, but communication schema between front-end and back-end.
Anybody else wants to?
Bindings to resources.
Bindings to resources, yeah. I wrote down these random words. So it's an application programming interface, that's the acronym. It's a description on how we talk to a system or how systems talk to each other. It's an abstraction layer between your system and other systems. Well, a web API is usually over HTTP, and you'll be serializing your data with JSON or XML, and you'll be doing REST or something else, maybe you're doing SOAP. So that's what a web API is, so to say. So let's quickly write a little web API. So let's say we want to write an API, a very simple API with just one endpoint that lists users. It's really complicated. So we have some user data type with a name and a skill. We can serialize them to JSON and from JSON. And we use our favorite web framework, Scotty, not Servant, to define it. So we have a route, the user's route. What we do is we get all users from the database. We set the content type of the response to applications.json, and we send the JSON encoded bytes to the client. Okay, so if people want to use our server, it's usually really useful if they know what endpoints they can call and how they work. So we provide some documentation to the user. We have a get endpoint for the user's resource, and we have an example of how the resource response looks. And maybe we'll even go crazy and give our users a JavaScript client that can interact with the web API. But where exactly is the API? That's the question we want to answer now. And it's kind of implicit, like it's in 3 places at the same time. We have the server implementation that implements some routes and some handlers for those routes. We have the documentation that documents those routes. And we have a client library that can call these routes. But now, say you have a few routes implemented, but not all of them are documented, then those routes are never going to be used by anyone. Or if you have documented routes that were never implemented, that's not useful either. And also, if we make a change to the API, we'll have to change the server, documentation, and the client. And these things will get out of sync really quickly, and it's very error prone. So that's not really nice. So we could mitigate many of these issues by writing a specification of our API first before we start coding and writing stuff. So we have to really think about what resources do we have. Do we have users? Maybe we have a cart for shopping. Maybe we have a friend's resource. What kind of resources do we have? How are these encoded? Are we going to use JSON or XML? What parameters do these resources support? Maybe if we want to list all users, we want to limit this query that we only return 100 users. It's going to be a parameter. Which methods does a resource support? Can we delete users? Can we edit them with a put? Can we retrieve users? What kind of status codes are resources going to return? Like if there's a success, it's going to give a 200 status code or 201. Maybe we want some examples of usage in the form of documentation. So basically, specification is a very strict form of documentation, and then once we have an explicit specification, we can implement the specification, and we can write the documentation, and we can implement the client that interacts with the implemented server. This will still require a lot of discipline by your developers to keep everything in sync, even if you write down a specification very clearly. So yeah, it's still very error-prone, people make mistakes, and we want to automate as much as possible of this process so that we can avoid these mistakes. So Servant tries to fix this. Servant is a domain-specific language for describing web APIs. It's a web API specification language. And once we have such a specification written down, it can automatically generate the documentation for us. It can automatically create Haskell functions for us to query our server. It can generate JavaScript for us to query our server. And the coolest feature is, like, if we have documentation generation and Haskell client code generation, the only thing that we have to do is once we have a specification, we need to implement the server. That's the only thing we have to change once we change the specification. And what Servant does is, if you make a change to the specification, it will use the type system to actually check if your server implementation actually does implement the specification. And if you make a mistake, it will give you a compiler error instead of some weird runtime error of a route that didn't exist. So that's pretty nice. It's, I always include a meme image, that's what they told me. So this is the only one. But. So what would such a domain-specific language look like? What kind of features does it need to make a specification of a web API? It's an empty slide. Okay, let's first just think about what can we do with a resource. It's always a good thing to start with. We have multiple HTTP verbs. We have get, put, post, delete, patch. I think there are a few others, but 4 is fine for now. And we want to know what kind of operations we can do on an endpoint. So can we do a get, put, post, or delete? And we want to know what kind of type this endpoint returns. Does it return users? Does it return a list of users? Does it return a maybe user? Does it return a shopping cart, or a string, or a hint? So what we have a little grammar for describing endpoints. And we can describe, we can do a get and return a user, and it's encoded as JSON. Or we can do a post as XML with some credentials. It's a small DSL for describing endpoints. But endpoints themselves are not very useful if you don't have any routes to reach them. So we need a way of describing routes. So the user endpoint is going to live under the /user route, and the register endpoint is going to live under /register. So we introduced the dot, what's the English word, operator, to build up paths. And a path always ends in an endpoint. So you have a path, /users, /friends, /1, and then at the end you have the get that describes what kind of thing we're going to return, or a post that describes what kind of thing we're going to return on the route. But one route isn't really useful either. So we have another combinator which takes 2 routes and it makes a list of routes. So you can have multiple routes and multiple endpoints this way. So we can have a users endpoint where you can retrieve users, and we have a purchases endpoint in which we can retrieve our shopping cart and inspect it. Well, the last thing that we want in describing a web API is that we have all sorts of parameters that our resources have. For example, if we request a list of users, we might want to limit, add a limit query parameter so that the response will always be of length 3. Or we want to request a user with user ID 5, so that's going to be a captcha. Or if you do a post contains a request body, and we want to know what that request body is. Those are all parameters to our web API. And also the parameters also have types. So a query parameter of limit is going to be of type int. And a capture, which is capture a user ID in our case, is also encoded as an int. And if we have can do a post to the user's resource to register a user, then the request body is going to contain the username and the password, and the resource is going to return a newly created user. So that's the way how we can describe parameters with types in this domain-specific language. So put everything together, we get this. This is the entire DSL. Of course, this is not Haskell syntax. This is just an abstract description of how we look. So let's use this description language to build up a more complex API to get a bit of a guide of how it works. So our informal specification is we want to create, query, delete users. They should be encoded in JSON. This is version 2 of our API because the previous one was in Ruby and it failed horribly. So we prefix it with the v2 prefix, and we want to limit queries, whatever that means. It's not a very clear specification, so instead we make a formal specification in our newly created domain-specific language. So we have 3 endpoints. The first one is the endpoint that gets a list of users. So if we do a get /users, we will get a list of users, and it will have an extra parameter limit that tells us how many users we want. Next, we have a post on the /users resource, which takes a username and a password and returns a new user. So this will be the register endpoint to register new users in our system. And then the third endpoint is the get a single user. As you can see, we have types inside our domain-specific language. So we describe these paths, but we also describe what kind of types they're going to return and what kind of types they require to function. And this is why when we're going to embed this domain-specific language in Haskell, we're going to do this at the type level instead of usually what we do at the value level. So just keep that in mind when we start explaining these slides. So this is the entire DSL in Haskell on one slide. It's a bit dense, but we'll slowly go through it. So we have our different methods. It's get, put, post, or delete. And well, those are all just verbs. So you can abstract over that. Every verb has a status code, like a 200 OK or a 201 accepted. And every verb has a content type. This is a bit of what this means is a list of types, which are tags that tag. Let's go a slide back. What kind of content types this endpoint can output? So it can output JSON, but it will also do JSON and XML, and then the endpoint would be able to respond in XML and in JSON. And finally, we have the A, and that's the result type parameter. Yes, question?
Would it detect an error if you specify no content types?
Well, there is one case where this is valid, is when your API returns nothing. And we have a no content return type, and that will type check with an empty list. That works, yes. But only in that case. Yeah. So the A is the result type of our handler. Then next we have the operator that builds up the paths, which is just data A colon open bracket ABB. Then we have the combine two paths operator. Then we have our the request body parameters, the query parameters, and the capture parameters, and they're also all parameterized over the result type. That's the A. And the S : symbol is a bit of scary Haskell. In Haskell, you have value level strings, but you can also have strings in the type level. Like when this DSL lives in the type level, then we still have like string values inside there, and those string values are not values, but they're types, and they're types of kind, symbol. It's a bit scary. We won't need them a lot. They just look pretty when describing an API and when we need to do the routing. But that's where the symbol comes from. And then we define the kinds of data types that we support our encoding. So we have a JSON or XML. We could also add CSV or HTML. Okay, so well, here's another example. Don't know if I have to go through it, but I'll do it anyway. So let's describe a small to-do API. We want to get a single to-do. So it's indexed by an identifier. So to-do /3 will resolve. We capture that identifier as identifier ID with type int. And if we do a get on the to-do /3, maybe it doesn't exist. So we return a maybe to-do. We also want to query all the to-dos that are either done or not done. So we have the get to-do endpoint for that. It's the second one, with a query parameter that can either be done is false or done is true. And it will return a list of to-dos. And we have a post to add new to-dos to our to-do list. We'll take a to-do description in the request body, and then it will return the newly created to-do.
So is it time to ask a question?
Yeah, sure. Ask questions if you're...
So how will this maybe render in JSON? Will it be like now if it's not there?
I will explain this later, but this is just a specification. We haven't implemented the server yet, nothing. So currently, nothing will happen. But as soon as we start to interpret this DSL, we will have to call the right methods to serialize it to JSON or XML. But we'll come to it.
So,
yes.
Why there is a list of content types? What does it mean to have more than one?
Okay, so when you send a request as a client, you can set, in the headers, you can say what kind of content you want to receive from the server. And if you say, I want to receive XML, and the API supports both XML and JSON, it will return either of those. And the servant framework will just, you just give the servant framework a to-do, and it will take care of serializing it either to XML or to JSON, depending on the request of the client. So that's why you can have multiple response types. Yeah.
Can we refactor the to-do string in front of the alternative?
Yes, definitely. So what you could do is you could make a...
the path purpose, yeah.
Yeah, you could make a type prefix to-do API A, and then change all the to-dos in A's, and then make a prefix to-do API. But what you also could do is move the to-do, only mention the to-do once, then add brackets, and put all the different routes beneath that to-do. So that would look like, do you get the idea what I mean?
Yeah, thanks.
So that's also possible. Okay, now that we have a domain-specific language to talk about APIs, we're going to look at our first interpretation of our DSL, and that's generating documentation. So if our API data type would just be a data type with values, then generated documentation would simply be a function from API to string, really easy, right? But we don't have a value, we have a type, which is makes stuff a bit more complicated. We need to be able to refer to the type as a value, sort of say, and that's where the proxy data type comes in. And it looks a bit silly because it has only one value, namely proxy, but it carries type information as the parameter A. So you can have a proxy to-do API or a proxy user API, and those two won't type match together, even though they both have the same inhabitant proxy. So this way we can pass around types as values, which is useful later on in the next slide. So how do we interpret a type level term? This is a type, maybe doesn't look like a type because it has 1s, 2s, and 3s, but with enough language extensions, you do language dependent types in Haskell, and then you get this. We can say type 6 is add 1 to add 3 2. Yeah, that's 6, right? This is a type. And we want to interpret this to give us the result 6. So how are we going to do this? We can do this using type classes. So we have a type class as int, and it takes a proxy A and it returns an int. So it takes a type and returns a value, an integer value. And to interpret this expression, we define the following instance. If we have an asint A and an asint B, so to say we have two types that we can convert to an integer, then we can convert the whole thing to an integer by adding the two results together. Well, that has to be a small b, by the way, it's necessary. And turning a type level integer, so the tick 1, tick 3, and tick 2 to an int happens with a built-in function called netval, which takes a proxy 3 and turns it into a 3. So it takes the integer from the type level and moves it to the value level. And this way we can interpret the type level term as a value level term. So we can now use this technique to generate documentation from our API specification. The primary function that we're going to implement is the docs function, which takes an API, type level API, and is going to return a string, or text, or a question, or whatever you prefer. And we also have some helper type classes, but we'll explain those as we go. We have the toCapture type class, which is to print out help text about capture parameters. We have the toQuery type class, which prints out help text about query parameters, and the toSample type class, which prints out messages about the return types of handlers. So to define our interpreter, we can simply pattern match, so to say, all the different kinds of terms that we have in our DSL. So let's just start at the base case, namely we have a get, put, post, or delete. I only show get now. If we know how to turn the A to an example, to a sample, so we can convert the A to a string. For example, you could have, if you have an instance for user, that's toSample, this would give an example user JSON string or something. Then we can write a bit of documentation that says we have a get endpoint and an example response is show example. If we have a capture of an identifier, we can say the description of this is integer ID is the to-do ID. And if we have a capture followed by the rest of the API, then writing documentation about that is writing documentation about the API plus appending the string integer ID is the to-do ID. And if we have a path, so if we have a route, then we can turn that route into a string. So we get /users, /3, etc. and append the rest of the documentation to formal documentation. It sounds a bit abstract, but you'll get something like this. Like you get /to get status code 200, header blah blah blah, scored content types, query parameters with an example, and an example response. So this way you can traverse over types and return a string, and this way you can generate documentation. Of course, this is not the kind of documentation that you want about your API because it's not very clear or anything. So
this is all completely automatic.
Yeah, this is all completely automatic. So we follow the instances in this chat. Like we didn't give all the definitions, but this will all happen automatically. But you, oh yeah.
Can you generate Swagger files, Swagger configs from that?
Yes. There is also a toSwagger config type class, which will generate a Swagger file, and we can also automatically then post interactive documentation, in which you can click and do requests and that kind of stuff. Yeah, it's totally possible. But you can tweak the documentation a bit, because you can give examples and description text for the captures, the query parameters, etc. And this way you can customize the documentation. But the main process is automated. Well, the actual type in servant is it takes an API and it returns another thing called API, which is a tree with examples and strings that we can render to HTML or PDF or any format that Pandoc supports. So that's really nice. And also we can generate Swagger documentation and Swagger config files so that you can have a nice website that explains all your routes from your specification. So now that we have done documentation, it's time to write a server. So we promised type safety. So if we don't implement our specification, we should get a type error instead of a runtime error. And so the type of the server needs to kind of depend on the specification, so to say. But before we go to that, let's just think about what a server is in Haskell. In Haskell, we have the web application interface. It's sort of standard. Some people don't think it's a standard. Some people think it is a standard. That describes how a request handler for an HTTP server should look like. This is a simplified view. It's a bit more complex, but basically, a request handler for an HTTP server is something. It's a function that takes a request as an argument, and the request contains which URL is requested, what content type does the client want, what query parameters were included, what's the request body, what is the host, what is all the headers, that's all in the request, and then the server returns a response, and the response is a status code, and some headers, and a byte string that contains the body of the response. So if you want to write a little hello world server, then it's a handler that ignores the request, because we're always going to write hello world, and we respond with the hello world string. And then we have a simple server in Haskell. It's really easy. I think it's a really natural way to think about servers. So let's look at how we would implement something in Y in the web application interface, and what we actually want given our specification. So if we want to create a new user, register a user, it's going to be a function from request to response. And we need to get the request body, we need to parse it as JSON to a username and password pair. We then have to consult the database to register the user that will return a user type. Then we need to manually encode the user again to a byte string. And then we can send the byte string to the client that requested this request. But what we actually want is, all this scaffolding is already defined in our specification. We already know that we have a request body that's going to contain JSON and a user name and password pair. We already know that we're going to return a user encoded as JSON eventually. That's the information we know. So ideally, our server should just be a function from username and password to user. That's what we would want, ideally. Let's say we have some hypothetical addition server that takes any of the query parameters that you give the route and adds those together and returns them to the user. That's also a function from request to response, just like registering a user. That's exactly the same type. But ideally, we would just want it to be a function from int to int to int, and then just implement it with plus. That's what we would want as Haskell programmers. And we can actually do this automatically by, again, interpreting the API type and doing all this scaffolding automatically. So we want some kind of type level function that takes our API description and returns a handler type, so the type of our handler. So for the addition example, we would want to have a function calculate handler that takes a hypothetical function that takes the query parameter int get int and returns into int. And calculate handler for the body user password get user should return user pass tuple to IO user. And the combination of those two APIs should return the two types combined. So this is another reason why the DSL lives in the type level, because in Haskell we can define these kind of functions. They're called type families, and there are functions on the type level. They take types and return new types. And the calculate handler function actually exists in Servant, and it's called the server type family. And we'll go through this implementation now of the server type family. The type families are basically just functions, but on the type level. So you have pattern matching, and you can return things based on what you match. So we're just going to start at the base case. Say we are at the endpoint, so at the end of the route. We have a get, or a post, or a put, or a delete, they're all the same. Then the A is our return type of our API specification. So our handler type should also return an IOA, or in Servant's case, accepts the servant error IOA, because we can also fail and return error code and kind of stuff. If we have two endpoints in our specification, so that's the OR operator, then the type of our handler is going to be either the type of the left-hand side or the type of the right-hand side. If we traverse a path, so we have a symbol on the left hand of our operator, and on the right-hand side we have the rest of the API, well, a path doesn't contain any type information, so we just ignore it and just return the type of the sub-API. If we have a request body of type A, that's an input parameter, then the type of our handler function is going to be A to server API. And the same counts for a query parameter. If we have a query parameter, then our handler function should be maybe A to server API, because maybe someone doesn't provide a query parameter, they don't have to. So this way we can systematically calculate the types of our handler functions. We'll go to a little example here. So we have an API description of a counter API. We can get the current value of the counter, which is an int. We can increment the counter, and we can set the counter to a specific value using a post, using a put. So it's either a get, an increment, or a set. So what is the type of the handlers of this API going to be? Well, we simply follow the implementation of the server type family. So the server of counter API is simply going to be the server of the get, the increment, and the set. And as we've seen in the previous slide, that just means calculating the handler type of the get, calculating the handler type of the increment, and calculating the handler type of the set. And that ends up in the handler type of get, which is an IOInt, the handler type of increment, which is IOInt, and the handler type of set, which is int to IOInt. And this way we can calculate our handler types. So a bit more advanced example, a to-do API again. We've already seen this example. And say we have 4 handlers that we've implemented. So the to-do get, which returns a single to-do given a to-do ID. To-do get all, which returns all the to-dos, but either all the done to-dos or the not done to-dos. A to-do create, which creates a new to-do in our database, and a to-do delete, which deletes a given to-do. These these types of these handlers are exactly the same types that the server type family is going to calculate. So this expression is going to type match. However, I made one slight modification, and now it doesn't type check anymore. And maybe someone can see it, maybe not. It's a very mean typo.
List of to do example.
Which one? This one?
Yeah.
This is
There's a list of to-dos.
yes.
The second one, and there is no list in the.
Yes, very good. So this is an error that we would want Servant to catch, right? So we have a specification that says that get all to-dos should return a list of to-dos, but our handler is not doing that. It's only returning a single to-do. So we don't want this to happen at runtime. We want this to be a strict compiler error. And it is. the GHC compiler will tell us, hey, I couldn't match to-do with list of to-do in the expression server to-do API. It doesn't really tell where it is because it's not smart enough to do that. And it will give a very long time error. That's a bit scary, but at least it will tell us that there's some problem with our implementation. And then we see, oh, wait, to-do get all should return a list of to-dos. And we fix that, and now we know that our server implementation is the same as our specification. So how do we run these handlers? Well, we have a nifty function called serve, which takes our API description, that's the proxy API. It takes our handlers, so server API is the type family that calculates the types of our handlers. So the arguments to serve is going to be all the handlers that we've implemented. So we're going to give endpoints as arguments to serve, which is the 4 handlers that we've implemented. And it will then return a Y application that we can run. And what the serve function will do is it will look at the type level stringlet rules, and based on those, route the right request to the right handler, and do all the scaffolding of decoding and encoding the JSON or the XML for us automatically. We'll quickly look at how this could be implemented. So this is also an interpreter. So again, we're going to use the type class way to write interpreters, just like we did with the documentation type class. What we want is we take an API description, we take our handlers, and we should return an application, which is a function called request to response. Well, to implement a get, that is simply rendering the return type. So we use the render function to render something to a byte string. So we can either render to JSON or to XML based on how we've tagged our API, or both. That's also possible. And we'll simply send the byte string over. That's all that a get has to do. If you just have a get, then it's just whatever the handler returns, we encode it, and we send it to the user. If we have a path to traverse, we need to make a decision on which handler we need to call, etc. So what we do is we have a path, we mention a path. We look at the text value of the path. So the path is a type level literal. It's a type level string. But using the symbol vol function, we can bring this back to a value level string, which we can inspect. And we're going to see if the path of the request starts with this string. If it does, we know that the route is matching. So we traverse on the right-hand side of the API and start consuming the rest of the API specification. If not, we throw an error and it aborts. So that way we know that the path, so we either end up recursing or we abort. And what servant does is, as soon as it sees an abort, it will try a different route and a different route and a different route until it finds one that works or it aborts altogether. So we also have server instances for captures and query parameters that will extract the query parameter from the request and put it in context of the handler, and one that extracts the capture from the request and put it in context, etc. So we have lots of has server instances for that. We can also derive Haskell clients automatically from our specification, which is a little bit easier, luckily, but it has a similar paradigm to how documentation generation works and how server generation works. So this is how we would use client. So client takes an API description and a base URL that says where our server lives. That's useful. And it will return a client API. And the client is again a type family that will return the types of our client functions. So we have a to-do get function that is returned, and a to-do get all function that is returned, and a to-do create function that is returned, and a to-do delete function that's returned by the client function. So we can say to-do get all, to-do create, to-do delete is client of to-do API. And it will automatically, through recursion, build up these functions, and you get all the functions to query your API for free. And you can use them in your REPL immediately. I can do to-do get of ID 3, and it will query the database through the server and return a to-do. We can query all the to-dos that are not done yet, which is give a talk in New York, which I'm not going to do, and fly home. The client type family is, yeah, question.
So when generating these clients, we're bound to some kind of like a transport library that's below, right?
Yes.
That needs to be done. Can we switch those, or are those like?
We now use HTTP client, I think, and it's fixed. So you can't change the underlying client. And I wouldn't really see a reason for it either, because there's not too much to tweak about it. You get a function with a type, and it will do all the calling underneath. Mm-hmm. So I don't really see why it would be useful, because they're going to send the same request anyway to the server. So
I mean, it could be reasons because of error handling or whatever. But
yeah,
it's
just yes.
You can control the connection pool, for example.
Yes, in the real implementation, there's an extra manager parameter, which contains the connection pool.
In the real servant?
Yes. Yes. So we do reuse connections and stuff in the client implementation. But I left it out for simplicity.
And to get JavaScript, do you pass this thing through GCJS, or is it?
You could do that. That works, sort of. The problem with that is HTTP client depends on the network package. The network package has native bindings to Unix and Windows. Those don't work on GCJS. So we added CPP, Magic, and shims and stuff to do that. But what we actually, I'll get to that later, to how we generate JavaScript code.
Okay.
It's one slide. Let's see. Okay. The type family for clients is basically identical to server, because a server handler is the same, needs the same information that a client sends. So you would expect those to have the same parameters. They're like duals of each other. And we have a, let's see. Yeah, that's all I want to say in this slide, I think. So this is basically exactly the same as the server type family implementation. The real implementation is a bit more complicated because we have a connection pool that we need to keep track of, etc. But I won't bore you with those details. So interpreting our API to generate clients can also be done with type classes. It's exactly the same trick. First of all, let's start with the get, which is in the middle. If we end with a get in our API description, then the only thing we can do is set the request method to get and run the request with anything that's inside the request data type. If we have two different clients or two different endpoints, then we simply return the client of the left endpoint and the client of the right endpoint. Return both of them. And if we have a path to traverse, we added the request to append to the path. So we just take the request, which has a field path, and we just append symbol ball s to that path. So when we go into recursion and we finally reach a get, then we send the request to the right path. And we have similar instances for all the other combinators, but they are pretty much similar. Like the query parameter combinator will edit the path to add a question mark to the end, and the parameter name and the value. JavaScript generation is basically what we currently do is exactly the same as documentation generation. It's a function from API to text with a JavaScript generator argument. So it's just that you can generate either jQuery code or Axios code, or AngularJS modules. I think that's the 4 that we have now. We also have a similar function for generating Ruby code, and there's a Python requests generator in the making. So given your API specification, you get all these kinds of language bindings for free, which is really nice. What we can also do is generate a mock server. So based on specification, and given that all our data types implement the arbitrary type class from QuickCheck, we can just pull a server from thin air. So it takes an API and it returns a server with all the handlers, and it will just create handlers that just generate garbage, but correctly encoded garbage such that the client can consume this, for example, for integration tests or testing your client implementations. Which, of course, are probably already correct because we generated them in the first place. But if you wouldn't do that, then this is really useful. We also have a servant QuickCheck, in which you can describe QuickCheck properties, which are then automatically tested for all the endpoints that you've declared in your server. So it will just start randomly generating requests, send it to your server, and just check if the QuickCheck properties hold. And this is really nice for saying, I want not a single route to ever return a 500 error under any circumstance. And it will just start fuzzing the server with random requests until it crashes. I only want JSON objects to be returned, even though I send XML. You make a QuickCheck property for that. You can make a QuickCheck property that all your handlers always return a cache control header. And this is really nice for, like, you write one test and you can test all your servers that you've ever implemented. And that's, I think, is really cool and really useful. Furthermore, we're working on authentication. This way you just have another combinator in the servant DSL. And on the server side, it will automatically derive all the code needed to check the JavaScript web token, see if someone is authenticated, and pass in the user object automatically. And on the client side, ask the user for credentials, and then build up the request in such a way that the request is authenticated. This is also all automatically, so you get good authentication out of the box for your APIs. That will be coming soon to Servant. We're working on that right now. And that's basically all I have for today. And if you have any questions or you want to start hacking on Servant, Haskell Servant.readdocs.io contains a lovely tutorial. And our GitHub is github.com/Haskell Servant. This is where you can check out all the packages. And there's also, we have like 3 example packages, one for Stack and Cabal and everything, so that you can start with an example project really easily. So that was my story. Thank you very much for listening. Yes?
Could you talk a bit about limitations of this approach? Was not implemented, and why is that? Is it possible? Like, for example, multi-part request handling or something like this?
Yeah, there are some limitations. People, for example, stuff with streaming resources is not really well supported. I think there is a servant multi-part package that does some of that stuff. Well, one of the bigger limitations that I've had until now, like we wanted to use this in our company, but there was no real story for authentication or authorization, which is something that is really essential. As soon as you make a public-facing API or even a non-public-facing API, you should always have some sort of authentication. And we hacked that together by putting some Y middleware in front of it. Like, the cool thing is Servant just returns the Y application, and there's lots of tooling for Y, for cache control and authentication and who knows what, and you can just plug it into Servant if Servant itself doesn't have the type safe functionality. Furthermore, the type errors are pretty scary. Like it says, if it works, it's beautiful, but as soon as it breaks down, you get a type error of like 300 or 400 lines. and that's not really nice, and you'll have to look at the type error for half an hour to figure out what is happening. And I'm trying to fix that now, because in GHC 8 you can do custom type errors. And I'm trying to find ways to improve the error messages that way, by implementing custom type errors if you miss certain stuff in your specification. Another thing that I think is a limitation is that if you have overlapping routes, say I have /users/3 and /users/capture int, those two will overlap, and servant won't give an error. It will just make a left biased choice and never call your capture handler, but always call the handler that doesn't include the capture router, which is a shame. And I've did a thesis to fix that with dependent types in Idris, but I don't know if it is possible in Haskell. So that's a limitation. So there are still, like, your specification could be wrong, and there is not a specification that checks the specification. That's a problem. Yeah.
Can you go back to the slide with the client generation on the first slide?
Yes, of course.
Yeah.
This one? Yes.
So you have to provide tag definition for each method?
No, you can leave that out. I just did that for documentation purposes.
You can send them this way.
Yeah. But so you can just leave this out and only do this one. That will totally work.
Okay.
But I thought it was clear to put it in there anyway. But you don't have to give the type definitions. Not yet.
Do you think it would be possible to adapt it somehow to other transports, like WebSockets, for instance?
You can use WebSockets, but not in a type-safe way. We have a combinator that is called raw in our DSL, which is basically a black box that evaluates to the type request IO response. So you can just plug in any Y application as an endpoint. So I use that to hack in a WebSocket. We don't have a story yet for type-checked WebSockets. And I think it's a bit of a difficult problem as well. Like there's basically years of research on session types, and every year new papers on that get submitted. So it would probably be something with session types, I think, or maybe something a bit easier. But for now, I think if you need WebSockets in your API, then you can do it, but you lose the type safety, but it is possible. But if you have any ideas on how to make it more type safe, I'd love to talk to you.
So, if you came so far that you can generate code for server just on specification, then we can maybe go one step further and generate API specification from database schema, for example. Like,
yeah, I think these kind of things are possible. Maybe not in Haskell, but in the dependency type languages. I think, for example, F# has a thing called type providers. And what they can do is it's a compiler plugin that can read in JSON data or CSV data or any kind of data, and it will recognize structures and generate a schema, and based on that schema generate types automatically. So you give it 5 example JSON files, and then it knows the type of that JSON, and then it can type check the JSON at compile time. So F# does this kind of stuff, and I think we might be able to do it in Haskell as well, or at least dependently typed Haskell with some text.
Yeah, there is actually a Haskell program that connects to Postgres and then gives out an API.
You can do anything with them at Haskell, just because you can do I/O in splices, so you can read some files and generate types.
But then you mean with template Haskell or something?
Yes.
Yeah, that could be possible. So.
I'm not saying that it's a good idea. But,
yeah, maybe it's not a good idea. But for example, Idris has a compiler plugin, also called type providers, in which you can generate types, universes, which depend on I/O actions, and we'll just execute those I/O actions at compile time once. And this way you can have like type safe, template Haskell-ish stuff, which is pretty nice. So I think there's lots of research to be done in this regard. It's exciting. Oh, yeah.
For example, if I have 5 query parameters that are shared by several routes, can I pull them out into the type and pull the handling of them out and
yes. Just open it. So you're saying we have something like type API.
Can you make a video?
Better?
Yes.
Okay, what we could do is so you could do this. You could just extract the common part into a separate type, and then you just interpolate the type inside there. That works. Okay. So yeah, this is definitely possible. So you have variables at the type level. Those are type synonyms, and just like you could split up stuff at the value level with variables, you can split up stuff with type synonyms at the type level, which is a very natural way to. You can also parameterize over stuff. You could even we can add the type parameter here, and we can say type user API is API user. It also works. So you can do all these kinds of weird abstractions to abstract over your specifications, which is really cool.
But I think that what he meant was that if you can pull those x and y,
You still have to repeat the params time.
Oh,
yes,
no, you.
Like for example, have a tuple of x and y as a parameter to your handler function.
Wait, I'm not sure if I understand the question. Wait, so.
If I do this,
yeah,
I still have the 2 parameters at the third level in every handler.
Yeah, true.
So
yeah, I maybe this would work as well. I have to think about it. I think this would work, and then you would only have to handle them once, and that's result return 2 new handlers. But I'm not sure. We can check afterwards if that works. I'm not sure. But I think what you mean is that you don't want to handle those parameters for each handler that you have. Like, don't have to repeat yourself in that way.
yeah, for example, they should be parsed into some record together.
Oh, I like the record. Okay. It's currently not possible,
So
but
there
might
might
be
be
interesting.
custom combinator and server instance for it.
Yeah, I think you could make a combinator for this, especially with the new language extensions with like record types and stuff. I think you could make a combinator for this that works, that generates a record.
Because handlers get parameters positional.
Yeah, positional arguments, yes.
If I have this x and y, then the first argument will be x and the second will be y.
Yes, exactly. And you don't know which one is which, it's positional based. But type level records is a new feature in GHC8, and it would be cool to experiment with this if we could turn it from positional arguments to record arguments. That would be interesting to look at. But not implemented yet.
Are there any future GHC extensions that you are looking forward to?
Custom type errors? Oh, you mean future, not implemented yet?
Yeah.
Dependent Haskell?
Okay.
Yeah, I know a lot of people are against it, but I think I haven't read the entire paper yet. It's a bit scary. They introduced like 5 new quantifiers, so you have for all and sigma and special sigma and special this, special that, many edge cases. But I think it will create a whole new world of fun hackery and weird stuff, so it's always good. Yeah.
The validation you talked about, the duplicate overlapping rules. I think you could do this with just like families.
Yeah, maybe.
Maybe verbose, but
Yeah, you could construct a proof that they don't overlap with our families, or make them not overlap by construction. It would also be interesting to do. But if you have ideas, share them with me.
So just a nitpick, you have encoding for your request body and content.
Yes.
And return commit, but you don't have an encoding for your query params. This is like by read or?
Oh yeah, we have a from query parameter type class, which takes care of parsing query parameters, because it doesn't really make sense to have JSON in a query parameter or XML. So it's like the read type class, they're pretty similar. Yeah.
Thank you.
Yep.